I'm not very cool with being lied to, and it seems that everything is a lie. So, playtime's over for me. I don't do much of the things I used to do. There's thousands of boats out on this lake now, right now, fishing. That used to be one of my passions in the summer.
Yes, that's Orion, lined up just off the horizon. Orion, his faithful dogs, Canis Major, Canis Minor, together hunt. That is, from a flood of waters. For Orion rises in the winter season and troubles the sea and the land with waters and storms.
Rock me, baby, one called him, sir. He knows everything.
What? You went over my helmet?
Well, not exactly over, sir. More to the side. I'll always call you first. It'll never happen again. Never, ever.
Oh, shit.
No. No. Please. No, not that.
Yes, that.
Whoa!
Ionization. We now know what alpha, beta and gamma actually are, but it still took years to understand that they were dangerous and why. The reason why is because they can all ionize neutral atoms. So what is ionization? Well, it's turning a neutral atom into an ion, or a charged atom. And the way radiation does this is by knocking electrons out of an atom. So, alpha, beta and gamma can all do this, but it turns out that alpha does it easiest, followed by beta, with gamma being the worst. Now let's see why. First, let's look at alpha. We should remember that an alpha particle is like a helium nucleus, and therefore it has a charge of +2. An electron has a charge of -1, and we know that opposites attract. So as the alpha goes past the atom, it doesn't need to touch the electron to knock it out. As long as it gets close enough that its electromagnetic attraction can pull on the electron, it can pull it out of the atom. So let's draw a line on the diagram showing how close an alpha needs to be to cause ionization. Now let's look at beta. We should remember that beta is an electron. Same charge as the electron that it wants to knock out. So we know that like charges repel or push each other. So the beta is going to repel the electron in the atom. Now, it's only got a -1 charge compared to the alpha's +2, so it needs to get much closer for its electromagnetic field to push on the electron. Also, a beta is much smaller than an alpha particle, so it has that disadvantage as well. Hence, it must get much closer to the electron to cause ionization. Let's leave a line on the diagram for how close the beta needs to get to cause ionization. Finally, we have gamma. Now we should remember that gamma is an electromagnetic wave and so has no charge. Because of this, it has to score a direct hit with a tiny electron to cause ionization, and hence it won't cause ionizations as often as alpha and beta. So let's recap. Alpha is the best at ionizing because it's big and it has a large positive charge, so it can cause ionization even when it's quite far from an atom. Beta is the next best as it's small, it's got a negative charge, so it needs to be fairly close to an atom to cause ionization. And finally we have gamma, and this is the worst at ionizing because it needs to directly hit an outer electron in an atom to cause ionization. It's very important you learn how good alpha, beta and gamma are at causing ionization, as it's very important in the rest of the radioactivity topic.
It's not time to party. Let's all cry, oh small baby that got shot in the head. Jose, it is just an illusion, an abstract confusion caused by drugs in my blood. near my waist. She was born without her days. Skinny white girl on the block. This life that we're wasting, rotten food we are tasting, naked thoughts in my head.
I have here a Plantarella, a modern day reproduction of an experiment that's actually over 100 years old. The Plantarella was originally designed by a Norwegian space physicist called Christian Birkeland, who in 1899 led an expedition to the top of an Arctic mountain to study the Northern Lights, or the Aurora Borealis as they're also known. Birkeland was actually the first man who really started to understand how the auroras were formed, and back in his laboratory in Oslo he built this experiment to show his ideas to the world. This particular Plantarella was designed by CNRS in France by a French scientist called Jean Lilliston. And it's a vacuum experiment. So what we have here is a vacuum chamber and a vacuum pump, which is a bit like a Hoover at home. And the vacuum pump sucks out most of the air out of the chamber. Not all of the air, but most of it. So it's recreating the conditions about 100 kilometers altitude where we see the aurora. Now inside this vacuum chamber, you've got a big ball here that represents the sun, and a small ball over there that represents the Earth. And within this small ball we have a really strong magnet recreating the Earth's magnetic field. The next thing we do is we put a voltage from the sun to the Earth, and so we're drawing electrons from the sun towards the Earth. Now this recreates the solar wind of charged particles that is always flowing away from our sun and into interplanetary space. Now when these solar wind, or when these charged particles come towards the Earth, they get trapped onto the Earth's magnetic field lines and they get funneled into the northern and the southern polar regions. And when they get to the northern and southern polar regions, they collide with the gases that are there. And what they do, they excite these gases and they actually give energy to the electrons within them. When these electrons relax, they give out light at the characteristic frequencies, thus creating the aurora. That's basically how the aurora is created on Earth, and similar to how the aurora is created on all planets that have a magnetic field.
Or maybe I should get myself a new tattoo. The liar, somebody who's known or someone who I admire. The liar, forget it, lady. That individual will move. The liar, be another liar. Mighty man with deadly heart disease.
Light is magic. There is magic in the way it is created, in the way it travels, the way it behaves. And beyond the magic of light itself, there is the magic of science, finding new and amazing uses for light, the life giver. Sunlight is a mixture of several different kinds of light. Most familiar is the visible light, the kind of light we see and see by. Then, as modern sun worshippers know, sunshine contains an invisible form of light called ultraviolet. Ultraviolet light produces tan skins and those healthy little things called vitamins. Science has learned how to produce this invisible form of light artificially. And now, without leaving our homes, we can turn winter into summer. The scientific ultraviolet light generator is arranged to remove all of the visible light and project a strong beam of invisible black magic light. One of the most amazing things about ultraviolet light is its ability to help us see things which by ordinary light are impossible to see. The radiations of pure ultraviolet light produce a strange effect called fluorescence. Fluorescence is a glow such as is found in the figures of an illuminated clock dial. Many different chemicals respond to the radiations of ultraviolet light. Different chemicals seem to respond with a different glow. This fluorescent effect makes it possible to read many secret or hidden messages. The ink with which the hidden message is written seems to glow under the magic rays. By the same principle on altered documents, erasures and changes may be brought out so that the attempted alteration is clearly visible. Mixed in with the visible sunlight and the ultraviolet light is another magic light that our eyes cannot see, but which we can feel as heat. These invisible rays of heat, which form so large a part of sunshine, have been given the name infrared light. Infrared light has no visual effect on our eyes. So in order to see its results, we must use a camera containing a special film which is sensitive only to infrared light. To furnish invisible light for the infrared camera, we will use these big electric units which produce no visible light at all. And now, for the first time on the motion picture screen, we are going to see a picture made entirely by infrared light in a dark room. There go the lights. And here is the picture taken by the infrared camera. And remember, to the eye, this girl is in total darkness. Infrared light is very penetrating in its effect. With it, for example, we can even take the young lady's picture while she's hiding behind a screen coated with rubber. The magic light shows that even a brand new shave isn't good enough when you are posing for the infrared camera. It digs right down and finds the whiskers that haven't even sprouted yet. Previews a shave 3 days in advance. Visible white light has also been put under control by science. A remarkable new device splits light into separate narrow rays so that the path of a beam can easily be followed. Notice that a light spreads out from its source in all directions. We can see how a mirror reflects light, how a prism bends the rays in different directions, and how light can even be bent around corners in tubes and pipes. Now let's see the effect of a simple reflecting surface used to control light. The rays leave their source, strike the reflector, and bounce back on themselves in the same path. Then if we place a lens like this in the path of the light, the rays are bent inward. Now let's try another type of lens, similar to the lens used in automobile headlights. Instead of bringing the rays together at a point, this lens bends them so they go out in parallel lines. In the motor car headlight, the new system of light control makes use of the type of reflecting surface called a parabolic reflector. No matter at what angle the light rays strike the reflector, they are bounced back in an even parallel path. The actual mechanics of this new headlamp are somewhat similar to previous two-beam lamps. When we are driving in the country, light from the central filament is used, and an intense beam of light is reflected straight ahead and far down the road. When we switch to the passing beam, another filament only a few thousandths of an inch away is lighted, and the beam is now aimed down and to the right of the road. A more accurate lens has been designed to direct light farther ahead in the driving beam, and more light on the right side of the road for the passing beam. Then the whole unit has been sealed airtight, so that air and moisture, tarnish and rust cannot cut down its efficiency. And so today, we drive with headlights that apply the latest principle of scientific light control. Headlights suited to the speeds at which we travel. On the high road, controlled light makes possible safe speed because we can always stop within the range of our own headlights. In city driving and in passing other cars on the highway, our controlled passing beam continues to light the right side of the road without shining in the other fellow's eyes. If we drive safely and always dim our lights when passing, we can take full advantage of the new control science has given us. And in the laboratories of today, science is working on the light of tomorrow, seeking still more numerous ways of using it to make life for all of us better and safer. Who knows what miracles are yet to come from the amazing development of visible and invisible light when the magic light of tomorrow comes into its own.